In this video, we will discuss the first of two methods that we will encounter for finding the volume of a solid object. This is something we will refer to as the washer method, and when we get to our second example in a bit, we'll see where this washer terminology is coming from. So I've included this picture where we have some solid, and we'd like to calculate what its volume is going to be. And the idea is we're going to want to set up a definite integral that's going to give us this desired volume. And if you think about what we've done with a definite integral, the idea is to take an object, such as this surface we're dealing with, a solid, and instead of directly calculating its volume, because it's not something that has a nice geometric shape, what we are going to do is apply our process to it. It's sitting above the interval from A to B, so we're going to take that interval and break it up into a bunch of equally spaced subintervals, where the width of each subinterval is this delta x that we've used before, b minus a over n. And then what we're going to do is cut it up into a bunch of small slices. And these small slices that we cut it up into are going to be washers. And the idea is that once you've cut it up into a bunch of these small washers, if we can approximate the volume of one of them, then what we do is we add up all of those volumes and it approximates the total volume. So in this case, we would say that the volume would be approximately equal to the sum from I equals 1 to n. And what we need to do is approximate the volume of one of these little washers. So the washer, if I draw it with a slightly different orientation, is really going to be just a cylinder with a small height. So the height of the cylinder in this case, or washer, is delta x. And if we can calculate the area of its top, in this case let's just call it A of x sub I, then the volume of this small washer is going to be the area of its top multiplied by its height. So if we do that for each one of these washers, we get an approximation to the entire volume of the solid. And if we want to get the actual volume, what we do is we take a limit as n goes to infinity, and as we've seen, that takes the limit of a Riemann sum, and it makes it an integral. It would be the definite integral from a to b, and what we would be integrating is just a of x dx. Where note in this case what that a of x is, it's just the area of the cross section, or the top in this case, of the washer. So let's put this to work in a few concrete examples. So in this example, we're going to use this washer method to determine the volume of the solid obtained by revolving the region bounded by y equals square root x from x equals 0 to x equals 1 about the x-axis. So first, just let me note that what we're going to be looking at is something called a surface of revolution, which is something we're going to work with quite a bit in the next two sections. And how we form a surface of revolution is we take some enclosed area, so in this case y equals square root x from 0 to 1, and we form a solid by revolving that object, in this case around the x-axis. So to give you an idea of what this will look like, when we revolve this around the x-axis, that entire area, it's going to turn into a solid. And the solid that it's going to turn out to be would be something that looks roughly like this, a parabolic looking type bowl opening to the right. And this is a solid object. And what we would like to do is calculate its volume. Now, using this washer method that we've introduced, the volume is going to be the definite integral over, in this case, how the x values vary, because we're thinking of our solid as going from x equals 0 to x equals 1. And what we are going to have to integrate would be the function a of x dx. Where, remember what this a of x is representing. It's representing if we start off at some x value between 0 and 1, and for that x value, if you think about what's revolved around the x-axis, this line, it turns into, in this case, a circle And the area of this circle is going to be the a of x. So let me just draw the circle to the right here. We'd like to calculate this area. And in order to calculate the area of a circle, all we need to know is its radius. But looking back at our original picture, what we revolved around the x-axis to form this circle is going to be its radius. So the radius, in this case, is simply this height, which is square root of x. So the radius of this circle is square root x, which means its area is pi times the radius squared. So pi times square root x squared, which is pi x. So now that we've determined the area of one of these cross sections, pi x, we go back up to our integral formula and we insert that. So this would be the definite integral from 0 to 1 of pi times x. So once again, what we've done here is we've formed this solid of revolution, and we said if we want to calculate its volume using this washer method, we think in this case of it as something going from 0 to 1 in the x direction. And what we've done is we've broken it up into these kind of vertical slices, where if we can calculate this area a of x corresponding to an x value between 0 and 1, that is what we need to integrate. So the antiderivative would be pi over 2x squared, evaluate it from 1 to 0, and this value, the volume, is pi over 2. Now once again, just like when we were calculating areas, the answer that you give should not be negative. So here having a pi over 2 seems okay. Let's look at another example. Let's determine the volume of the solid obtained by revolving the region bounded by the curves y equals x cubed, y equals 8, and x equals 0 about the x-axis. So let's first just sketch the region that we are going to revolve. So if we think y equals x cubed, so roughly speaking, something like this. Then we have y equals 8, say a horizontal line. And then x equals 0 is simply the y-axis. So the region that we are going to rotate about the x-axis is now shaded in. And when we rotate this region around the x-axis, I'm going to sketch a picture of the solid. And just like other pictures we've drawn, they do not have to be perfect, far from it, but what they have to do is kind of get that relevant information across. So we're taking this shape and we're revolving it around the x-axis. So it's kind of mirrored over here to the bottom, and then we have the top. So how I would explain this, because I know my picture's not the best, is I'm thinking that this object that we have here might be something that looks kind of like a solid hockey puck, so a solid cylinder. And what we've done is we've kind of hollowed out this shape from the middle of it. So if we want to calculate the volume, we can take the same approach that we did previously. We can think about how the x values vary. So y equals x cubed and y equals 8 intersect when x is 2, because 2 cubed is 8. So you're going from 0 to 2. And what we need to integrate is this function a of x. So to get a of x, we think if we have an x value between 0 and 2, so the region sitting above it would be this line, we take that line and we revolve it around the x-axis. And when you revolve that line around the x-axis, what you're going to get is an annular type region sitting in our solid. And let me draw that picture outside here. You have a larger outside circle and then a smaller inside circle. And the area we would like to calculate would be the area of this thing we call an annulus. And an annulus is just a geometric object where you have a larger circle and you've subtracted a smaller circle from the inside. So what we need to do is think about, what quantity is going to represent, let's say, this little radius, I'll call it little r, and what quantity is going to represent this big radius, big R. And going back to our original picture, that little radius is going to be determined by this space going from x up to the first curve. So the little radius in our picture is going to be that distance, so little r. Likewise, the big radius would be the distance up to that second curve. So that would be big R. So in our case, it looks like big R is 8, the distance from the x-axis to that furthest curve, and little r would be the distance from the x-axis to the closest curve, x cubed. So a of x, the area of this annulus, you take the area of the larger circle, pi times 8 squared, and you subtract away from it the area of the smaller circle, pi times x cubed squared. So that would be pi times the quantity 64 minus x to the 6. And this is the reason that we call this the washer method, because this area that we're calculating here, it looks like it's the area of, say, the top of a washer. So putting this together, what we need to anti-differentiate would be 0 to 2 pi times 64 minus x to the 6. So pi is just a constant that pulls out front. The antiderivative of 64 is 64x. And the antiderivative of x to the 6 is 1/7 x to the 7th. And this is going from 2 to 0. So we plug in a 2, so 128 minus 1/7 times 2 to the 7th. We put a minus sign and we plug in 0. But when we plug in 0, we get back 0. So the value of this volume is given by the quantity here.